Right. So I think that this talk is actually a little bit of overview of quantum information, well, quantum communication, well, secure quantum communication. So essentially, I would like to tell you about maybe a little bit like my own journey to quantum crypto and secure communication, um, but the outline of the talk is like a searching for the limits of privacy and randomness, which is kind of associated topic. But essentially, what I'll try to answer in my talk is there such a thing like ultimate privacy, ultimate security of data, and if so, what's the role of quantum physics in it? And so that's sort of like the theme. But I would like to take you through some historical development of approach to security and privacy. And then after that, I will talk a little bit how quantum physics helped. And then the next stage, of course, would be what's next? Like, can we implement certain things that are certain quantum solutions that are really cool, and is that something practical? Can we really hope that we achieve the ultimate security, ultimate privacy in our life? So that's the plan. So without, sorry, I just still came from another place. So I'm still like trying to calm down by my desk and sort of got into a swing. So if you hear me breathing, it was because I was running up the stairs. Okay, so the outline of the talk. The first question is there such a thing like a perfect cipher? Can we communicate with perfect security? Then another topic that I'll cover very briefly in order to explain the notion of a perfect cipher is a cryptographic key. I'll say a few words about the key distribution. That's like the holy grail of cryptographers. So if you talk to guys who are into data security, they would really like to know whether there is such a thing like a secure key distribution. And so we'll talk about this. And then I'll talk about quantum physics, how it comes to the rescue, how it solves the key distribution problem. And then I'll just go a little bit ballistic, talking about the notions of reality, security, and some kind of philosophical connections. So if you're like a hardcore physicist, you will probably not like this, the very last bit. But if you like speculations, that's kind of fun. So, okay, so basically when it comes to secure communication, if we take sort of a historical perspective, so people started communicating in a secret way as soon as people came up with the alphabet. And the essential tricks that we use in secure communication is to write something and then do a little bit of a permutation of characters in your message, or do some substitutions. Or you can even combine permutations with substitutions. So for example, when it comes to permutation, we know that the oldest crypto device that was sort of in use about 400 BC in ancient Sparta was a device called a scytale. It just implemented permutation of characters. So imagine that you have a wooden button of a certain diameter, like a cylinder, and you take a part of parchment, right? So kind of a ribbon that you wrap around this cylinder here, and then you write a message on this. So just, for example, attack tomorrow. Then you unwrap it. So when you unwrap it, you can see at the bottom of the screen that it just implements kind of permutation of characters, right? When you unwrap, the letters appear in different locations. And then you give this parchment to a military courier that will take you from one military commander to another military commander in ancient Sparta. So the guy will just run with this parchment. And when it arrives at the destination, the receiver will have a wooden button of the same diameter. So the guy, the receiving guy, will just simply take the parchment, wrap it around this cylinder, and the message would reappear. So, very simple, but it's the first mechanical device that we know to perform very simple operations, permutations, and in the crypto settings, but was probably the first mechanical device to implement a very simple operation like permutation on a string of numbers or characters. When it comes to another technique, substitution, so we do know that it was used by Julius Caesar, allegedly, if you were to believe historians. I don't know how much they really know, but apparently it's kind of semi-documented that Julius Caesar communicated with his military commanders by using a substitution cipher. Basically, for each letter from the Roman alphabet, he would substitute another letter. And the rule was actually that was used apparently was very simple. You just take the alphabet and shift it by 3 characters. So like I just demonstrated here. So you take your alphabet, you write all the letters from the alphabet, shift to the left by 3 characters, append those 3 sticking out letters, and then you have a substitution rule, right? So you just, for A, you substitute D, for B, you substitute E, for C, F, and so on and so forth. So that's how you would then encrypt the message "attack tomorrow." So that's even today that kind of simple substitution ciphers we call Caesar ciphers sometimes. Now, so you may think that when it comes to substitution ciphers, if you are prepared to drop the shift by 3 rule or implement substitutions in any other way, then of course the difference between substitutions and permutations or just one-to-one mapping is just blurred at this point. So we have actually a staggering number of those substitutions. If you consider any possible substitution, any one-to-one mapping of the alphabet to the alphabet, if you take those, so then you would have actually, 10 to 26 or something substitutions, a huge number. So you may think, okay, well, if we just drop a simple rule like shift the whole thing by 3 characters, it will be too much really to deal with any brute search or anything. But actually it is not. It turns out that one-to-one substitution cipher is very easy to break, and that was figured out pretty early, actually, in the 9th century by a Persian, a man of all talents. You know how it was in the 9th century. This guy actually worked in Baghdad, so he was a philosopher of the Arabs, known as Al-Kindi. So those days, they used to do just about everything. So he was a polymath. But one thing that he did, he figured out that in any natural language, the distribution of characters not uniform. So that means that if you write in a natural language, the frequency of letters is not random. So for example, in most Indo-European languages, the letter E is the most common letter, and followed by letter. So here we have a distribution for English language, for example. The E is the most common, the second comes T, and then letter A is very common, and so on and so forth. And certain sequences of letters, like TH, for example, are quite common as well. So he had this insight that if you look at the statistic of characters in a cryptogram, then you should be able to figure out what it really represents. So the most frequent character, whatever it is, should represent the letter E if you take English language text, a regular English language text, and encrypt it. So that's very clever if you think about it. The probability theory, you may think like from today's perspective, it's not a big deal, right? But in fact, bear in mind that he did it in the 9th century, right? And it's only in the 14th century or so that people started playing with probability properly. So not bad, right? So he came up with the idea how to break those one-to-one ciphers. They called monoalphabetic ciphers. This is one-to-one substitution. And of course, just for fun, let me just mention that we are talking about the distribution of characters is only applicable when you take a representative text. So your sampling should be representative. There are writers who like to show off that they have a perfect command of language, and they write something that is called a lipogram. A lipogram is a text where you on purpose drop a certain letter. It's actually a really tough exercise. So you take, for example, an English text. It's very difficult to write avoiding letter E, for example. So here's the lipogram. The first one you can see is just a paragraph where the letter E is dropped. So you don't, you can read it. It sounds okay, but but it's not trivial. But probably the most famous lipogram was written in French. In French, actually, the letter E is also the most common. So Georges Perec, he managed to write a huge, book, a reasonable book, without the letter E in it. It was translated to English, and the translator managed to also translate it without putting the letter E into the text. Another, you can actually look up for the lipograms. It's kind of a fun to play with lipograms. I'm sure that there are lipograms in Russian as well, and this kind of Al-Kindi method wouldn't work with lipograms, right? So we are talking about a representative text. Right, so the question then is, we have schedule, we have substitution ciphers, and the question is, can we construct a perfect cipher? So we know that the substitution ciphers can be broken by Al-Kindi method if it is a one-to-one. Can we do something about it? Can we improve ciphers so that no statistical analysis will get it right? So the short answer to this question, whether there is a perfect cipher or not, the answer is, well, yes, there is a perfect cipher. It's called the Onetime Path. So if you write, so here is a simple illustration of it. If you write a message as a sequence of zeros and ones, so we assume that we pick up a known digital alphabet like ASCII code. So the message, when it's encoded in 0 and 1, is transparent. Everyone can read it. And then imagine that you have those two characters that I'm going to introduce, Alice and Bob. It will be much more difficult to explain things in quantum information science without Alice and Bob. So Alice is going to communicate with Bob. So she would like to send messages to Bob. And she will take a message, a sequence of zeros and ones, and then she will pick up. And here comes the first important notion that I would like to communicate, the notion of cryptographic key. So we have a completely random, absolutely random string of zeros and ones that Alice has. You can see it on here in red, right? So the key is then added to the message. So Alice takes the message is of a certain length. You take the key that is of the same length, and then you just add the key to the message bit by bit. So basically, you take 0, so you can see that the first bit of the message is 0, the first bit of the key is 0, so 0 plus 0 is 0. And so the addition is modulo 2, which means like a regular addition apart from the fact that if you have 1 plus 1, so you have to stay in the set of 0 and 1. So 1 plus 1 is equal to 0. So that's you can think about it as XOR, logical XOR operation or addition modulo 2. So then, you get a cryptogram, a sequence of zeros and ones. Now, the cryptogram inherits the randomness from the key. So if the key is truly random, then the cryptogram is random as well. So you see, in the process of addition, the whole randomness from the key is sort of transferred to the cryptogram. You can prove it, but intuition is easy in this particular case. So you have a cryptogram, which if the key is truly random, the cryptogram is equally random. So no statistical method whatsoever will work on this particular key because on the cryptogram, sorry, because it's a random. It looks like a randomly chosen set of zeros and one. So Alice then sends the whole thing to the cryptogram to Bob, And in transit, you can listen to, or you can intercept this transmission, but what you'll see is essentially a sequence of zeros and ones, which are truly random. No statistical analysis will help you here. But you know, this looks like random to everyone except Bob. Bob has the key, has exactly the same string of zeros and ones as Alice. So he takes the cryptogram and adds the cryptogram to the key and recovers the message. So the key is used for encryption and decryption. So Alice is going to use the key for encrypting the message, and Bob is going to use the key to decrypt the message. The key, and it was actually proven by Claude Shannon, that as long as the key is truly secret, truly random, known only to Alice and Bob, of course, and never reused, then the whole thing is secure. So no statistical analysis whatsoever can break this cipher. So we do have a perfect cipher. We do have a perfect way to communicate, except that there is, you know, there's always but to the whole story, so to this narrative. So what is the but? So we have a perfect cipher, but we have to distribute the key. And the key can be used only once, and once you start reusing the keys, that's a big mistake that can actually be, then the statistical analysis can kick in. So in this case, we have to make sure that Alice and Bob have the big supply of those cryptographic keys, so that you can meet, for example, in secret in one location, agree on a number of bits identical in secret, keep those keys in a very secret location all the time, and then use them only when they want to communicate. But of course, you know, sooner or later they will run out of the key because they are not allowed to reuse the key. In this particular case, the problem is, okay, so what will they do if they are in two different locations miles away from each other, right? How would they then establish this key? How would they just make sure that they have the identical sequence of zeros and ones that are truly secret, that are not known to anyone else but to them? So here is the problem that we are going to look at. And you know, the key distribution problem, as it is known, is a big thing to cryptographer, to secure communication, and basically in this quest for perfect secrecy, we already have a perfect cipher, Onetime Path, but we have the key distribution problem. So we have to fix this problem. How do we fix this problem? There are two ways essentially to fix it, and one is actually to avoid this problem, is just to go into another set of ciphers that are known as public key systems, which I'm not going to describe here, but this will be like a separate lecture about this. But in those ciphers, you simply don't distribute the key. They are based on a certain mathematical problems which are difficult to solve. They are not proven to be absolutely secure, but you can show that breaking those ciphers is as difficult as solving certain mathematical problems. And so this kind of security is based on the area in computer science, which is called computational complexity, where computer scientists divide problems into difficult problems, easy problems, and using those mathematical problems, for example, problems like factoring large integers, you can upon those problems, you can build public key crypto systems which do not require the key distribution, because in fact you have two keys. One is a public key that is used for encrypting messages, and a private key that is used for decrypting messages. And public key can be shared, but the private cannot. I will not go into these details. Lots of interesting mathematics, lots of interesting physics, because we know that quantum computers, as soon as we have them, can in fact break most of the public key crypto systems. Not all of them, but most of them. So the big challenge today is to design public key crypto systems which are secure or resistant to quantum attacks. So that's ongoing topic of research. So I'm not going, as I said, I'm not going to go into that direction. Instead, today I'm going to talk about quantum cryptography, which is another way of fixing the problem. So we're going to look at quantum phenomena for that would help us to distribute the key. And essentially, in this box, we have two methods of doing it. One can vaguely say is based on the Heisenberg uncertainty principle, and that was proposed by two colleagues of mine, Charlie Bennett and Gilles Persat. There is an issue with that thing if you want to really push the whole thing to the limits, in a sense that you want to talk about perfect security, then those ciphers are fine as long as you trust the devices. So you have to be sure that nobody actually hacked your devices that you are using. So you have to be sure that you know what you are doing, and you trust the hardware that you may have purchased from someone else. So another one is based on entanglement, which I proposed back in '91, and that one can be made device independent, so you don't even have to trust the devices. So that would be of interest in our sort of discussion where the perfect security may go. Okay. By the way, if you have, I don't know what kind of format. You can ask me any questions anytime or later, whichever you prefer.
No, let's do it later, just
okay,
at the end of the lecture.
Good. Yeah, but if someone, if there's a dramatic call for explanation at any time, I'm always willing to stop and answer the question.
Okay.
Okay, so again, I was not preparing this talk. I was not entirely sure how much mathematics, how popular I should make it, and so on. But given that it is condensed into less than 1 hour or so, then I cannot go and explain everything in mathematical details. I can give you a bit of a flavor how things work, but you have to then just go look up and work things yourself. So I'll just skip through mathematical details and just try to convey the concept so that you understand the global thing, how it works, and then you can feel the gaps yourself. So essentially, in the key distribution problem, we would like computer scientists, of course, came up with all kind of interesting mathematical techniques that that allow Alice and Bob to do things such as, if they distribute the key, those keys are not identical, they can do the error correction over public communication. And as long as they know how much information an eavesdropper may have upon the key. So here you have Alice and Bob having a key called X, and an eavesdropper that may have some approximation to this key. The guy, whoever was eavesdropping, got some bits right, some bits not quite right, and some bits didn't get at all. So the thing is, if Alice and Bob can put an upper bound on the amount of information that eavesdropper has about those binary strings, then there are beautiful mathematical techniques known as a privacy amplification that can actually reduce the value of the length of X, the key that Alice and Bob share, but exclude Eve completely from the game. So let me just show you the basic idea how it works. So suppose, consider 2-bit key, right? So Alice and Bob establish the key, and it has 2 binary digits, which I call X1 and X2. So you can see X1 and X2. That's not multiplication, it's a binary string. X1 is 0, 1, and X2 is also 0, 1. So it's a binary string. And of course, there are 4 binary strings like that, 0, 0, 0, 1, 1, 0, and 1, 1. And suppose Eve knows, somehow Alice and Bob figured out that Eve knows at most 1 of the 2 bits, right? So Eve may know either X1 or X2. They're not sure which one. So it could be that an eavesdropper knows X1 or knows X2. So the question is now, how the privacy amplification technique would work in this very trivial case. So one thing they can do, Alice and Bob can simply do binary addition of x1 plus x2. So they add, this is the same kind of addition that we saw when we talk about the encryption. So they add x1 plus x2, and they get 1 bit of information. Call it Z here, right? Now, this Z, so now they can claim that they have a secret Z. So the eavesdropper has no idea with, what the value of Z is. With probability half, it could be 0 or 1 from the perspective of the eavesdropper. And the reason for that is that, essentially, so suppose eavesdropper knows only x1. Then you add it to this x1 unknown binary value. So this probability have you either flipped this binary value or you didn't flip. So therefore, that's just eavesdropper has no information whatsoever about Z. However, Z is only 1 bit. So you see, this protocol here, again, this is just to give you an idea how the privacy amplification works. So this protocol starts with a key that has 2 bits of 2 binary digits. And Alice and Bob, in this process, shrink the key to 1 bit. Z is only just 1 bit. But they reduce the amount of information that an eavesdropper may have about the key from 1 bit to 0, essentially. So there's a price to pay, but they also gain something. So the thing is, the key distribution doesn't have to be perfect. There could be errors there. We have techniques, mathematical techniques to handle errors. And so here comes a little bit of mathematics, but I'll just keep it, and I'll skip it as well. The main problem, in order to bootstrap the privacy amplification, is that Alice and Bob have to estimate how much information an eavesdropper knows. So for example, in this trivial example that I gave you, they knew that an eavesdropper knows at most 1 bit of information. Maybe nothing, maybe 1 bit, but not more. So that is actually important to start the privacy amplification. If you don't have this information, it's tough luck. You simply cannot use it. So that's a bit of a problem. So the question is how to find out how much an eavesdropper may know. In classical physics, it's essentially impossible at the fundamental level. And we'll show that we have quantum techniques which allows you exactly this. So you can estimate how much someone else may know about this. Now, what kind of intuition then should you have? Why, quantum allows you to tell such a thing like, even though you don't know any method of eavesdropping, but still you can make a statement, no matter how someone acquired this knowledge, I can still be able to detect it and estimate the amount of knowledge that person acquired. Yeah, well, if you want to have sort of like a basic feeling for that, it just goes back to the essential principles of quantum physics. So you know that in quantum physics, if something can happen, right, we cannot just add probabilities, we add probability amplitudes for this to happen and then calculate probabilities by taking mod square of those amplitudes. So for example, in this diagram, if something can happen in 2 mutually exclusive ways, and I just put probability amplitude for this alpha 1 and for this alpha 2, you add those 2 probability amplitudes, you take mod square, and then you can see that we have a part of a classical physics, so we add probabilities, but then there's an extra term that is called interference term. So essentially whole quantum physics is nothing else but studying this interference term here. Now, there is this simple rule that this only works when nobody is watching, right? So the quantum physics happens when nobody is watching. Once you watch, or you have a partial information, which path was taken, whether this system evolved from here to here, from initial to final state via this path or that path. Once you have this kind of information, then this interference term disappears. You affect seriously the interference term. And so this is essentially what we do in quantum crypto. Essentially, we know that if someone looked, then there will be interference or certain correlations that will be destroyed. And from the destruction of those correlations, we hope to estimate the amount of information that person gained. And so we are going to use entanglement, and if in sort of the usual scenario, we would just distribute 2 qubits in a highly entangled state. Those could be polarized photons, that could be any objects essentially that you can entangle. So if you prepare 2 qubits in entangled states, 0, 0 plus 1, 1, and if there is no eavesdroppers, so here on the left, I can just have the state of the 2 qubits and tensor product the state of some device, an apparatus, or state of knowledge of an eavesdropper. If those are completely separable, right? So if the state, if those things are, if an eavesdropper is disentangled from this state, then Alice and Bob will see perfect correlations, as we'll see in a moment. However, an eavesdropper may want to gain some knowledge, whether it is 0 or 1 that is going to be registered by Alice and Bob, trying to entangle itself or just a probe or a device. So you may have a term like 0, 0 tensor product E0 plus 1, 1 tensor product E1. So in this case, an eavesdropper got entangled himself or herself or itself, depending what kind of device was used, and you create a more complicated state. Now, those 2 states do not have to be E0 and E1 do not have to be orthogonal, so it may not be a perfect knowledge. But nonetheless, that's something that we hope that allows us to sort of figure out whether how much information Eve may have. So Alice and Bob then testing correlations in sort of looking for correlations in a certain basis can figure out how much Eve knows if that is what happens. So let me actually, I will come back to this problem later. So let me actually skip this one bit. Yeah, well, okay, so that's roughly the idea. So the idea is, remember what we want to achieve. What we want to achieve is we want to distribute a sequence of random numbers, a sequence of random zeros and ones to 2 individuals, we call them Alice and Bob, in 2 distant locations. And we hope to use entangled states, so highly entangled states, so that of the type 0, 0 plus 1, 1. So the 0 and 1 can be encoded in, say, polarizations of 2 orthogonal types of the polarizations. And we want to estimate the amount of interference, because that would give us some kind of knowledge how much information could have leaked to a potential eavesdropper in the process of distribution of this key. And from that, we are going to use privacy amplification to recover the key. So the key part, of course, is to figure out, to put an upper bound on this information, how much knowledge an eavesdropper may have. So historically, so this slide basically shows that historically the different approaches to cryptography, and the field probably started by Stephen Wiesner in early 70s, who had sort of an idea how to use quantum phenomena for producing unforgeable money. And this idea was then taken by Charlie and Gilles, who turned it into a key distribution idea. And so that's a class of crypto called quantum crypto called prepared and measure. I independently came up with the whole thing, and I use entanglement, but the two techniques are very much related in the sense that whatever you can do via prepare and measure strategy, you can also do in an entangled way. Not necessarily the other way around, but you know, the entanglement takes you further, and that's why I'm just talking about it. Not so much because I want to, you know, prey on my turf, but it's just, but it is a more powerful technique. So the way you know, I started thinking about it was actually, it goes back, in fact, to reading some Asian almost papers. So here's a paper that Einstein wrote together with Podolsky and Rosen in 1935, where Einstein was unhappy about the quantum physics, and he was trying to come to terms with those different statistical predictions. In fact, there are statistical predictions in the first place, hoping to find more precise description of nature and coming up with some paradoxes. So in this paper, what attracted my attention was that Einstein was talking about something that he called an element of reality, which sort of was defined that if in any way disturbing a system, we can predict with a certainty the value of a physical quantity that is, then there exists an element of physical reality corresponding to this physical quantity. So here we have, you know, as a physicist, it may sort of sound enigmatic. What Einstein wants to say is, okay, give me a physical system, and there are certain properties that are quantified, and I can learn about this property. I can learn the value of a physical property without messing up the system. So then I say this does exist. So that means that the measurement, for example, recovers predetermined value of this physical property. But if you're a crypto person, then this reads as a perfect eavesdropping, as a definition of perfect eavesdropping, because that's exactly what an eavesdropper would like to do. If you can find a way of learning about a physical property that is carrying a bit of information or a certain value of information, a physical property in which information is encoded, then you basically have a perfect eavesdropping. So if the element of physical reality corresponds to perfectly eavesdroppable system, so to speak. And so, of course, you know, let's try sort of maybe explain it using a polarization of photons. So as you all know, polarization is an intrinsic property of a photon. So we cannot just measure a polarization, but we can measure polarization with respect to some specified direction. So there are like zillions of polarizations, and we choose a direction, and we can say with respect to this direction, we have two values of polarization. So any measurement can give you two results, +1 or -1 in the units of h bar. So each photon carries a certain value of polarization in sort of one mental picture that we may have. Now the question is that essentially, you know, that was a part of the problem that Einstein was trying to figure out. The question was, do photons have predetermined values of those polarizations? So is it the case that each photon carries the value of polarization along all possible directions that you can choose to measure later on? So that when it comes to a detector, the photon already has this polarization, and what the device is doing is just simply uncovering the value of this polarization with respect to the direction. So is that the case or not? Well, the answer to this question is, well, it's not, right? And so about 60 years ago, John Bell came up with the idea where this philosophical sort of statement by Einstein is actually a testable proposition. So it's something that you can refute the existence or predefined existence of a certain properties. And so this is maybe one piece of mathematics that I'll just go through because it's important. So Bell came up, and this is actually a simplified version. It's not exactly the way how John Bell thought about this Gedanken experiments, but sort of like a thought experiment that John Bell had in mind was of this type. So imagine that you have a source that is producing two photons. One photon goes to Alice, the other photon goes to Bob. Now Alice and Bob are physicists, and even they will become experimental physicists in a moment, but for now they're just Platonic physicists. You know? And Alice is going to measure a polarization of each incoming photon, choosing randomly between two directions, A1 or A2. And Bob is going to do the same, picking up his two directions, B1 and B2. Now, if A1 is chosen on Alice's side, then there are only two outcomes of the measurement. So A1 can be equal to +1 or -1. The same for A2, the same for B1, the same for B2. So think about it as a binary random variable, right? So you have a random variable that has two values, +1 or -1. Now construct another variable, random variable S, that is a linear composition of A's and B's. And you can see expression for S here. And if you look at it, you can see that if it is indeed the case that in each particular realization of this experiment, you can attribute values to A1, A2, B1, and B2, then S can only take values +2 or -2. That's easy to see, right? So because if B1 and B2 are the same, then one term here is 0. If B1 and B2 are different, then the other term is equal to 0. So altogether, it seems that it's easy to see that S is equal either to +2 or -2. But of course, you know, if you repeat this experiment many times, then the average value of S is somewhere between those two extremes, between +2 and -2. And you can measure actually this value by, you go back here, you can estimate by estimating for, if Alice and Bob can just register the outcomes and can communicate in public, then they can estimate the average value of S. And the thing is that you can also do theoretical predictions, right? So you can use quantum theory, for example, to make those predictions. And the obvious fact that we stated here, that the value has to be between -2 and 2, is contradicted by calculations or predictions based on quantum theory. And again, relatively simple calculations can show you that you can actually have a bit stronger current, that the value, the average value, can go outside this interval -2 to 2. And it can even be 2 square root of 2 in the extreme case. So that's kind of interesting, right? So that we have two different predictions here. And hello, I can hear someone asking me a question, but I'm not sure whether this is a.
No, just keep it.
Okay, I keep on going. So altogether, with the benefit of sort of hindsight, you can actually say that today we understand it this way, that there are classical correlations which give you this S value. If you take the mod of S, that will just take you from 0 to 2. The quantum physics or quantum correlations will give you this figure of merit S or mod of S up to 2 square root of 2. You can even consider sort of more correlations that kind of don't allow you instantaneous signaling, but still would be just consistent with well, it would be consistent. It would be sort of like a hypothetical theory where correlations will not lead into superluminal communication. So that would give you even a higher value of S. But anyway, so the nature so far is only confined to S from 0 to 2 square root of 2. So there is this quantum regime here, and the question is, can we pick it up? And as we say, the quantum correlations do, if you find anything this S greater than 2, then you know that it is not the case that there are predetermined values for A1, A2, B1, and B2. So here's a very kind of nice picture taken during, I understand, discussion between John Bell and Alain Aspect, who was at the time contemplating the experiment, where you can see this 2 square root of 2 on John Bell's blackboard at CERN. And so Alain Aspect, well, many people later came up with experimental proposal, but the one that at least for me was like the most convincing one. There were other people before Alain who were working on setting up experiments. Some guys in California, some guys in Harvard, some guys somewhere else. And believe it or not, those experimental techniques to implement, to generate entangled photons, for example, and implement experiment in such a way that would give you any decisive answer was not easy. But perhaps Aspects was the first one that was very convincing in many ways. And Alain just reported it, S is greater than 2. So there are cases, at least, where there is no element of reality that you can associate with this photon or polarization of a photon. It is not the case that the photons do carry predetermined value of polarization. So if that's the situation, so we are almost in business on the crypto side, right? So because if the values do not exist prior to measurements, they are not there. They are not available to anyone, including eavesdroppers. So testing for the violation of Bell's inequalities is essentially equivalent to testing for eavesdropping. So that was intuition, right? So and then of course you have to do a bit of a mathematical gymnastics. You have to do error correction. You have to do privacy amplification. You have to show it in the crypto content. But the idea is there. So once you have the idea, the rest is a bit technical. I'm not saying it's easier, but at least you have a starting point. So what was interesting is that when you have this idea somewhere between physics and crypto, it's very difficult to if you work somewhere in between those two fields, it's very difficult to to have this work somehow recognized, because physicists don't quite get the crypto part, and the crypto guys do not quite get the quantum part, and that was actually in the early days that was the case, certainly. So I was working together with two people, John O'Rarity and Paul Tapster. They worked not far away from Oxford in a place that used to be called Defense Research Agency in Malvern. And we were trying to implement it, and we did, but for a long time we were not allowed to publish it because, well, not even so much because the admin thought it's supposed to remain secret and classified, mostly because in the UK, for some historical reason, anything related to cryptography is under the Foreign Office, and John and Paul were working in Defense Research Agency, which is under the Ministry of Defense. So the two ministries obviously don't talk to each other, and they were saying, oh yeah, this is crypto, you guys have to talk to another research lab which is under different ministry. The thing is that those guys had no idea about lasers and so on and so forth. So you see, the bureaucracy is exactly the same all over the world. If they can just mess up something, they will almost certainly will.
Artur, 5 minutes left.
5 more minutes to go?
5 minutes left. before the end. Okay.
Okay, so I'll just then. So basically, the whole thing worked, as so. Of course, when you just at the very beginning there were some assumptions about the whole thing. So, for example, the obvious assumption in the scheme is that Alice and Bob's labs are secure. There's no information leak from the labs. There is another assumption that Alice and Bob control and trust devices in the lab. And also that, because they have to choose randomly for each incoming photon in this particular case, if they test for the Bell inequalities. So they have, if you want to be philosophical, you say they have free will, or if you are an engineer, you say they have pretty good random number generator that make those random decisions for them. And the question is, can we get rid of any of those assumptions? And I will just only tell you that it is possible to design the, so if I were just to come to one of the latest development in the field, it is possible to design something that is called device independent. So basically, the protocol that is based on Bell inequalities is device independent. So you don't have to trust your device. Devices are sort of self-tested. You only have to look at the mathematics. It's just, it turns out that the statement about the violation of the Bell inequalities goes both ways. So if you see a violation of the Bell inequalities, say at the level of 2 square root of 2, it can only be achieved in a certain way. So there's a certain degree of robustness there. And that can be used to make a statement that as long as you see the statistics, those devices are okay. So you don't have to worry. You can buy them from the guys you don't trust. You can go to your enemy and you can get those devices. But if you run the test based on Bell inequalities and you get the statistics right, that means that those devices are actually okay. The statistics is doing self-testing for those devices. But this would be just like understatement, because you have to, there are many other assumptions there. For example, that if we do the key distribution, we don't use the device only once, we use it many times. And the big problem in improving the security of this device independent scenario was to actually go from the independent and identically distributed scenario, the IID scenario, to the general device case. And that was done in a beautiful work by those 3 people here. Rotten, who did most of the work. She was a PhD student of Renata Rene from ETH, and Thomas Vidi. So this is actually, to me, the interesting, almost the ultimate proof that the whole thing works. And so we can, to cut a long story short, we can get rid of the assumption that Alice and Bob control and trust devices in the lab. There's, of course, then the last one about the free will and those random choices. Do they have to really have a free will? And again, sort of, we can weaken this assumption a little bit, but we cannot just get rid of it completely. We can amplify the randomness of the random number generator, but what is important, we have to make sure that they're completely independent from the devices that we don't trust. So that's sort of, we cannot make the last bullet point green. We can make it perhaps yellow, but not green. So that's what we are. Well, is it the end of the worries? As I said, there is still this question of finding a way to amplify the randomness of your choices, but I think we know that as long as we have epsilon of randomness and some local resources, we can do it. So the quantum crypto today is an industrial proposition, not necessarily the device-independent part, but the conventional quantum crypto. And you can have it on land, you can have it in space. You can have it, the Chinese are probably leading the field in terms of a large-scale implementation from space. So they use satellites. They have a dedicated satellite, an issue satellite, that is sort of sending entangled photons into two different ground stations, which are like 1,000 kilometers apart. And so that's remarkable that we managed to get there. But I think there's more to go, and there's still more fundamental work to be done. And probably, many of you who are interested in this field, don't worry. Just it's not like it's all sorted out. There's still lots of work to work on. And if you want to know more, I think a good starting point is perhaps this semi-technical review of ultimate security that I wrote with Artur. That probably requires an update soon, but that would be certainly a good starting point before you start searching internet and trying to learn more. Anyway, so I think I exhausted my time, and thank you very much for your attention. My apologies for being late.
Yeah, thank you so much for the nice lecture, and we still have some time for the questions. Please take opportunity to ask founding father of quantum cryptography. Vadim. No questions?
I've answered all my questions the few previous times I watched this lecture. I have no questions. Already asked Artur all I could on previous occasions.
Okay. So, guys, everything is clear, yeah? I think. So, Artur, thank you very much once again. Okay.
Well, thank you. Thank you very much. It will be much more fun to be there and interact with you guys. But it is what it is. So hopefully next time.
Artur, maybe 2 words about situation in Singapore in your center. Could you tell us?
Yeah, well, I'm in Singapore at the moment, and I used to be the director of this Center for Quantum Technologies in Singapore. But I think after running the whole thing for almost, maybe 13 years or 14 years, I finally managed and succeeded to hand it over to my successor, Jose Ignacio Latorre, who's now the director. He's doing a fantastic job. So the center is good and growing, and we have lots of talking about quantum crypto. Many of you, I understand, visited, so at least some of you visited, so you're always most welcome. It's a fun place to be, and I think that on the secure communication side, there's Alex Ling here, who is working on satellite quantum crypto, so I'm sure that... And anyway, so if there are any questions, I'm sure Vadim will be able to answer, or Sergey will be able to answer if I'm not around. So you guys talk to them. You have fantastic specialists on your side.
Okay, so thank you very much once again, and good luck, Artur.
Thank you. Thank you. Pleasure.